Welcome again to another series of lectures in mechanics of deformable bodies. This time we'll be discussing axial force and axial stress analysis. So for the lecture objective, you have to solve first correctly the axial force in the body and investigate and design correctly the materials based on applied axial stress. We will be doing some discussion where we will discuss concept theories to obtain information from objectives 1 and 2. And you can have an open forum in the comment section, and we'll have the problem solving and finally an evaluation. So what we'll be needing for this lecture are calculators, notes and pen, and your references. So now let's formally start the lecture. Let us recall first what is stress. So stress is actually defined as the intensity of force applied in an area. And it is defined by the equation presented in your screen, that is P is equals to capital P over A, where this is the force and this is the cross-section of, this is the area where P is applied, and this one is the stress. So P here is an actual stress acting over this area. And we can also recall from mechanics that stress is actually not uniformly distributed. The resultant axial force may not be acting on the center of the area. This causes eccentricity and will cause a bending moment, and that will not be part of the lecture. We will just focus on force applied on the centroid of a body, as you can see in this figure. Now this P is causing a stress over this area, as you can see on the left side of this figure. So this P is acting on the centroid, causing a uniformly distributed stress on the area presented in this portion. So P again is acting on the centroid. And since stress is a unit of force over unit area, the units that is commonly used for metric, we have Pascal, representing Newton per square millimeter, megapascal, and GPa. Now, in US customary units, they use PSI, pounds per square inch, or KSI. In reality, stress is not actually uniformly distributed in some cases. And as you can see in this figure, we have a load P applied atop of this member in here. And if you will explore the cross section here, somewhere here, around half the value of the width of this material, a more concentrated stress is over here at the centroid. But as you go outside, or the outer portion of this material, the stress is less distributed. But as you go further away from the point of application of P, the stress is kind of distributed. And eventually, if you reach a certain point, 2.5 times, 2.5 times the width of this portion of this material, the stress can now be assumed to be equally distributed. So in this study, we'll just focus on this case where P is causing a uniformly distributed stress over the cross-section where it is applied. Now, for the procedure of analysis, we have to determine first the internal forces of members using equations of equilibrium, because the determination of internal forces allow us to determine the internal axial force, which will eventually lead us in analyzing the internal stress or the internal axial stress. So the equations of equilibrium is actually needed in this lecture. So those three are summation of forces along x equals 0, summation of forces along y equals 0, summation of forces along z equals 0, and summation of moment equals to 0. Now, after determining the internal reaction, or the actual internal reaction, we have to identify whether that actual internal reaction is compressive or tensile force. Compressive forces causes an object to shorten because it compresses the object. Tensile force tends to elongate the object because it pulls the object apart. So that is either compressive or tensive. Let's have a sample problem here to check our lecture or to apply our lecture. So it is asked here to determine the axial force developed in segments CD, BC, and AB. So we have here a shaft with 3 concentrated loads applied. We just have my pointer on my pen. So identify whether the internal force or the internal reaction for each segment is compressive or tensive. The only way we can identify the internal reaction in an object is to explore the section or the point where we want to determine the internal reaction. Now let's perform equilibrium analysis. So if we want to explore the internal reaction at segment CD, we have to pass a cutting plane between T and D, like this one. And then we will choose which segment we will be using. Is it the left segment or the right segment? This time we'll be using the right segment for a more simplified solution, but you can use the left segment. So if I use the right segment here, make sure I place all the externally applied loads and the support reaction. But since there's no support on the right segment, there's no support reaction placed in this free body diagram. Now, the internal reaction here should be exposed since we expose cross-section between C and D. So the internal reaction is the one that resists the internal reaction to prevent it from displacement. But in reality, all objects are subjected to deformation once there is an applied load. So the direction of the internal force is actually assumed, but it is very obvious that since there is a 30 kilonewton force to the right, so definitely the internal reaction is directed towards left. But if during our discussion, you will see that if the value that you have determined for this one is negative, that means that your assumption, the direction of your assumption is the opposite of the actual direction. Meaning, if you have a negative value of FCD later on, that means your direction is, the true direction of the internal reaction is not to the left, but rather it is directed to the right. So let's name the internal reaction as FCD because it is the internal reaction of segment C to D. Now, how can we solve FCD? As you can see, this is a collinear force system, so we can use summation of forces along X. So again, it is important for you to first look at the free body diagram and then evaluate what equations will you be using. So we have 3 equations of equilibrium, but for this case, we only need one of them. So that is summation of forces along X. Now the internal force for segment CD, which is FCD, is exposed and assumed to be in tension. In this case, this is assumed in tension because it is acting away from this point or from this plane. So it causes or it pulls the cross section, causing this segment to elongate, and that's the behavior of tensile force. Now let's see the value. Let's look for the value of FCD and check if this really is in tension. So performing summation of forces along X equals to 0, we have negative FCD plus 30 equals to 0. Then we can solve for FCD equals to 30 kilonewton. Now we have a positive value, meaning that our direction is correct. So this is proof that the internal reaction FCD is 30 kilonewton having a behavior of a tensile force. So meaning to say it is causing this portion is being elongated. Let's try to solve the internal reaction at segment BC. Now again, if you want to solve for the internal reaction segment CD, you have to pass cutting plane and then expose the internal reaction. This time I'm still using the right portion of the shaft, but You can use the left portion if you find it more simple, but make sure you have to replace this support with corresponding support reaction. Later on, we'll solve for the support reaction and we'll be using the left side. Okay. So now I'm about to expose the internal reaction. So this time I'm still assuming that this is in tension. So the internal reaction is FBC for segment BC. Again, if I have the positive value, meaning I have the correct assumption that this is in tension. Otherwise, if I have the negative value of FBC later on, that means that the tension direction is not the right direction, but rather it should be in compression. So the internal force for segment BC, what we call FBC, is exposed and assumed to be in tension. The value of FBC can be determined using summation of forces along X. We cannot actually use summation of moment because there's no moment in this one, and the forces are collinear. We cannot also use summation of forces along Y because there's no force acting along Y axis, so it's really just summation of forces along X equals to 0. So summation of forces along X equals to 0, we have negative FBC minus 20 plus 30. So we can now solve for FBC, that is equal to 10 kilonewton. So a positive value means that our assumption of direction of FBC is correct and that this internal reaction is in tension. So we have FBC equals to 10 kilonewton and that is in tension, or it is a tensile force. Now for the case of solving the internal reaction of AB, again we do same process. We cut segment AB and then this time I'll be using the left segment, but I have to replace this support with corresponding support reaction. Now you can solve for the support reaction by simply assuming a support reaction and then use equations of equilibrium. Now if you've done that, you will yield with an answer of 35 kilonewton. If you don't want to solve for the support reaction, you can use the right segment, but if you have already determined the support reaction, you can use the left segment, which is a way easier, or it looks more simpler than using the right segment. So again, I'm exposing the internal reaction. This time, I'm using a compressive assumption. So I assume that the internal reaction is compression and naming it as FAB. But it's very obvious that this should be in tension, but I intentionally assumed it in compressions to show you the case where the value will be negative. Okay, so this time, this is in tension. Now let's do the same procedure. Summation of forces along X equals to 0. We have negative FAB minus 35 equals to 0. And then we can solve for FAB. Now you can see that the value is negative, meaning the direction of FAB is not compression like what we assumed. Therefore, it should be in tension. So the answer, you have to correct that one, 35 kilonewton tensile force. If you get a positive value, that means your assumption is correct and this is compression, but it's very obvious from the beginning that it will not be a compressive force since it has to counteract the external reaction. Okay. Let's have another example where it involves cables. So we have here a crate having a weight of 300 kilograms carried by two cables as shown in the figure. We are to determine the internal tensile force developed in each cable due to the weight of the crate. So again, we start solving this problem by having the free body diagram of the structure. So if we want to get the internal reaction for cable AB and cable AC, we have to cut, or you can cut somewhere here or here and then draw the internal reaction, that is FAB and FAC. Now, observe, this is a concurrent coplanar force system. So for a coplanar concurrent force system, we only use summation of forces along X and summation of forces along Y equals to 0 because summation of moment cancels out everything here. So we are left with only two equations, but that's okay. We only have two unknowns. Those are FAB and FAC. So we can use summation of forces along Y and summation of forces along X, but you can see that we'll have two equations and two unknown for this one. Later on, we'll see. So let's draw now the weight. The weight is equals to 300 multiplied by 9.81, which is the gravity. So you have 2,143. So question is, which of the two equations will I be using? Summation of forces along x or summation of forces along y? You have to analyze. You have to be smart when it comes to thinking which of the equations you should be using. So if I use summation of forces along y, I will have two unknowns, the y component of FAB and the y component of FAC. So I have to think of another equation. So if I use summation of forces along x, I have unknown, the x component of FAB, and another unknown, the x component of FAC. So both summation of forces along x and summation of forces along y yields to unknown, but you have two equations. So it's either you use for summation of forces along x or summation of forces along y. So let's solve for summation of forces along y. So we have the x component of FAB. The x component of FAB is here. So that is negative FAB cosine 40 plus the x component of FAC is FAC cosine 60. So you can see the x component is not another unknown. If you count, it's not another unknown, and the FAB, the y component of FAB is not another unknown. You just have one FAB and FYC as unknown because you can express their components in terms of the resultant FAB and FAC. It's not necessarily you have four unknowns because two components for FAB, two components for FAC. It's not the way like that. So you only have two forces, then you have only two unknowns. As you can see that the x component, the only unknown is FAB. You don't write FABX or FACX. It's more convenient to express it in FAB. Now, we have to solve, or we have to look for another equation that involves FAB and FAC. But we cannot solve these two unknowns using only one equation, and that is by using summation of forces along y. So summation of forces along y, we have the y component of FAB, so that's FAB sine 40 plus FAC sine 60. Don't forget the load, minus 2,143 equals to 0. And that is your second equation that involves both FAB and FAC. So let's recall the two equations. We have equation 1 and equation 2. You can press that in your calculator. Some scientific calculators have the option of solving two equations, but you can use this one by expressing FAB in terms of FAC and then substituting this one to equation 2. So the method is up to you if you can use a manual calculation or you can use your calculator. So I've already solved for the values of FAB and then FAC. So I have a positive value of FAB, meaning that my assumption that FAB is tension because it acts away from point A. So I have 1,494 Newton as tensile force. So similarly, I get a positive value for FAC, that is 2,289.25 Newton. Again, it is also a tensile force because it acts away from point A. So there you go. You have now the internal reaction for cables AP and AC. So that's really our objective, to determine the internal reaction for each member. Just like what we did from the previous problem where we determined the internal reaction for segment AB, BC, and D. Let's have a sample where it involves a non-concurrent coplanar force system like this one. So we have a beam carrying a 50 kilonewton concentrated load at E, and it is supported by a hinge at C and a cable passing on a pulley at B at points A and B. So we are to determine the tension in the cable. So first we draw the free body diagram of the structure. Drawing the free body diagram involves writing down all the forces involved in the system. So if we want to get the internal reaction happening in this cable, we have to pass a cutting plane here and then expose T and P here. So we replace support condition with corresponding support reactions and try to observe that this force system is a non-concurrent force system, so we are allowed to use summation of forces along x, y is equal to 0, and summation of moment equals to 0. Now, we can use summation of forces along y, but we'll have two unknowns, t and rcy. We cannot use summation of forces along x because we'll have another two unknowns, that is the x component of t represented by t and rcx. But there is a much more convenient solution by using summation of moment about point c, because using the equation summation of moment about point c eliminates rc, y, and rc. So we have now the summation of moment equals to 0. That equation will cancel out rcx and rcy, and leaving us with only one unknown, that is t. So performing summation of moment will allow us to solve for t, but let's resolve first t so we can identify, or we can actually solve for the moment induced by this force. As you can see, this is an inclined force, so it is better to resolve this one anywhere along its line of action, provided that we can easily determine the moment arm. So in this case, point A or t can be resolved at point A, so that we have components tx and ty. So tx here is now eliminated if we perform summation of moment at point C, because it passes at the moment center, leaving us with only ty and t. But this doesn't count two unknowns because ty can be expressed in terms of t. So performing equilibrium analysis by taking summation of moment at support C, we have ty, the moment of ty is equal to ty times 8. We have it negative because it causes a clockwise rotation about point C, minus t multiplied by the distance 4 meters. That's also negative because it causes clockwise direction about point C, clockwise rotation about point C. Plus the 50 kilonewton force here causes a counterclockwise rotation about point C, making it a positive moment equals to 0. Now this ty can be expressed in terms of t, so leaving us with only one unknown. So having the component ty, we can solve for its resultant t by using this triangle. This is simply the slope, and the hypotenuse of the slope is square root of 20. So we have the value of ty is equals to 2 over square root of 20t. Now this equation has now only one unknown, that is t. This is a linear equation. You can solve for t equals to 22.49 kilonewton. So we have a positive value, meaning to say that the direction of our t, or the assumption of direction t, is correct. So there we have our first objective. We can now solve correctly the axial force in the body. Now this objective will allow us to attain the second objective, which is to determine the stress. Again, if you have now the value of force P, you can solve for the stress in an object. So the internal force determined from the analysis of structure causes the stress called working stress. You can see from the internal reactions that we have determined, the tensile force, the compressive force, they cause what we call working stress. So this is actually compared to the allowable stress of the material, which is the allowed stress the material can hold. So intentionally, we do not want the working stress to go beyond the allowable stress, because the material can no longer hold the working stress if it is beyond the allowable stress defined by the engineer or the designer. So in investigation, to know what is the working stress is actually the investigation part of this lecture. To do that, we need to first identify the axial force, and then we can subsequently solve for the axial stress by simply using the formula that is force over the area, meaning we are investigating. We know the geometry of the object or the cross-section of the object, You know the internal reaction, you know the cross-sectional area, you can identify the working stress. Now, on the other hand, in designing, you identify the axial force and then you know the allowable stress of material, but you have to design the geometry or you have to design the size of the material. So our lecture for this part of our objective for this part is to investigate and design at the same time. So investigate meaning we take a look on what is the stress that is happening in an object. Design is that we have to select the appropriate size or the appropriate material in order for the system to be working or in order for it to be structurally stable. So in designing, we do not want the working stress to actually go beyond the allowable stress. Theoretically, the working stress should be equal to the allowable stress. But we do not want the working stress to go beyond. So sometimes we assume, most of the time, we design the system such that the working stress will be less than the allowable stress. Otherwise, any factor or external factors such as the size of the member or error in fabrication will cause a greater value than allowable stress if you do not consider this one. So if you're designing such that the working stress will just be equal to allowable stress, any external factor or unforeseen external factor might cause sudden failure in your design. But if you have more of a factor of safety or you're designing this less than the allowable stress, then you can say that just a minimal external factor would not cause the allowable working stress to exceed the allowable stress. So that is taking into consideration a factor of safety, which will be part of the next lectures. So just this time, we have to design a system such that the working stress will not be greater than the allowable stress. So let's have the sample from the previous problem. So we have here a steel beam or a shaft that has that is loaded with 3 concentrated force, 25 kilonewton, 20 kilonewton, and 30 kilonewton. We have already identified the internal reactions for AB, BC, and CD. So it's listed here. Now, we are doing an investigation. We have to see what is the internal stress caused by this internal reaction. So first, the working stress in each of segment can be determined by the equation that the working stress is equal to the internal reaction over area. So for segment CD, the internal reaction is 30 kilonewton. This 30 kilonewton causes an internal stress by 30 divided by 170, you have 176.47 megapascal. Okay, so as you can see that the allowable axial stress is 200 megapascal. So if you press this in your calculator, you can multiply this one with 1000. So I've already converted the answer into megapascal since Newton divided by mm squared is megapascal. So you will not actually get 176.47. You multiply this one with 1000, so you'll have a unit of Newton and square millimeters. So if you multiply this one with 1000, you have 30,000 divided by 170 square millimeter, you'll get 176.47 MPa. I just directly converted the answer to megapascal. So you can express your answer in kilonewton per square mm, but it is more presentable to write your answer in megapascal for this case. Okay, so don't forget to multiply this 30 to 1000 to have your numerator expressed in Newton. Okay, so for the stress, you can see that 176.47, this is the investigated working stress. Now we checked the internal stress, 176, that is lower than the allowable. So we can say that this portion of the beam is safe from this load. Segment CD is safe. because it is smaller than the allowable stress. Now let's check segment BC. This time, segment BC, we have 10 kilonewton internal force. Divided by the area, we have 58.82 megapascal. So it's actually far lower than the allowable axial stress of 200 megapascal. So it is safe from this load. Now let's check stress for segment AB. So FAB is equals to 35 divided by 170. You have now 205.88 megapascal. And this one, in portion AB, the working stress exceeds the allowable stress. And that could be part of your investigation. So you can conclude that the working stress is beyond the allowable stress. And this is how you investigate the internal reaction or the internal stress in an object. Now let's do the design. The design portion involves selection of material and selection of size. Now here, you have an available material that has an allowable stress of 200 megapascal. So, designing the minimum cross-section of the beam, the internal force for each segment must be considered. But as you can see, 35 kilonewton is the maximum value of internal reaction for this beam. So, it is safe to use this 35 kilonewton because it will yield or will require most probably the highest value of area because it's the critical value of your internal reaction. Compared to other two internal reactions, this FAB will require material with greater cross-section. So using material A, that is 200 megapascal, we have the allowable stress is equals to FAB over A. So the area required for this beam to be safe is equals to 35,000 divided by 200 MPa. That is 175 square millimeter. Likewise, the cross-sectional area of the beam when using material B. Now, if material A is not available and you have an alternative material of 150 megapascal, then you can do the same manner. The area required is equals to force over the allowable stress. So that is 35,000 Newton divided by 150. And that is 233.33 square millimeter. Okay, so material A is actually has higher strength than material B. So this will require less area. On the other hand, since material B is weaker than material A, it requires a larger area. So using material B requires larger area than using material A. So this portion is designed because you are designing the cross-sectional area, you are selecting the material for the system to be working or to be in order or in safety. Let's try another investigation for the similar problem that we have solved. We have here a crate having a weight of 300 kilograms. Sorry for the typographical error. And we already know that the internal reactions for FAB and FAC is 1,494 and 2,289 respectively. Now let's investigate the amount of stress developed. Again, for FAB or for cable AB, the working stress is F over A. So stress at cable AB is FAB over here is the area of circle. So the diameters are given. So I consider the radius, that is 2 for segment AB or for cable AB rather. So force is equals to, this time I'm using the unit Newton and the areas are expressed in millimeters. So we have stress AB equals to 118.90 megapascal. For cable AC, we do the same calculation or investigation. The stress at AC is the internal reaction of AC and the area. So you have 2,289 divided by the area. You have 45.54 megapascal. Now, you have already investigated the internal stress happening in cable AB and AC. Now, let's try to design the cable. If we have a 180 megapascal allowable stress, if we're using a steel material for this cable having an allowable stress of 180 megapascal, it is required for you to determine how big will be the cable. So, recalling that the allowable stress is equals to force over area, we have now the allowable stress limited to 180 megapascal. We know the internal reaction for cables AB and AC. We can solve for the area and then eventually identify what should be the minimum diameter of each cable. So, for cable AB, we can solve for the cross-sectional area of cable AB by using F over stress or allowable stress. The internal reaction at cable AB is 1,494 divided by the area is 180 MPa. So that is equals to 8.30 square millimeter. Now, you equate this with the area of the circle involving B or the diameter, you get diameter equals to 3.25 millimeters. But in reality, you can round this up to millimeters so that you can say it is 4 millimeters. But then round down this one because this will be unsafe, causing the working stress to go beyond the allowable stress because you minimize you reduce the area. Now, in a similar manner, we can solve for the area required for cable AC, that is FAC divided by the allowable stress equals to 12.72 millimeters. And then you can solve for the diameter, gives you now the value 4 millimeters. And here, let's design another one. The maximum value of the contradilated E if the cable has a cross-sectional area of 20 square millimeters and an allowable stress of 200 megapascal. This is capital P. So the maximum tensile force, this is quite a tricky problem because you have to solve for the maximum value of P. That given the maximum value of stress that this cable can withstand. So to solve for the maximum value of P, we have to solve first for the maximum value of the tensile force that can be carried by this cable. So we will limit the value of P based on the maximum value of T. So the maximum value of T is based on the maximum allowable stress that this cable can carry. And the maximum internal reaction of this cable, which is T, can be defined by its allowable stress of 200 megapascal, having the area of 20 square millimeters. So the maximum value of T that this cable can withstand or carry can be expressed by T is equals to area times the allowable stress. You're just manipulating the equation such that you're solving for T. So that is area 20 square millimeter times the allowable stress of 200 megapascal. So the maximum value of force that this cable can resist is 4,000 Newton. This is somewhat an investigation on how much value of T or force internal reaction that material can carry. So that is 4,000. If the value of T is at maximum of 4,000, going back to the free body diagram, so this is the free body diagram of the object, we replace T with 4,000 and then we can solve for the value of T. So, substituting the value of T in this equation and performing summation of moment at C, that is equal to negative Ty times the distance is 8. Again, this is negative because it causes a clockwise rotation about point C, minus T times 4, again negative, causing clockwise rotation about point C, plus P times 2. Now, this is not equation 2 unknown because we already identified the maximum value of T, which is equal to 4,000. So, again, Ty can be directly solved since this is a component of T. That is 2 over square root of 20 times 4,000 times 8 minus 4,000 times 4 plus P times 2. You can solve now for P equals to 15,155.42 Newton, or convert that into kilograms, you have 1,545 kilograms. So now we were able to investigate how much working stress is developed in a material or an object, and we were also able to design correctly the material based on the applied axial stress. And we are done with our lecture. Thank you very much, and please grab some time to take a comment or suggestion for me to improve my delivery of lectures. Thank you very much, and have a nice day.